Okay, so we're going to start 9-1 right now. So we're going to look at the significance test, the basics here. All right, so a significance test. So it's just a formal procedure for comparing observed data with a hypothesis whose truth we want to assess. So again, we did this example right here. We just have this procedure here, and we're trying to test a hypothesis, okay? So here's another example. Can Jack be confident of victory? So Jack is feeling fairly confident he'll be elected by obtaining more than 50% of the vote. So they talked to a random sample of 100 voters who shows that 56 will vote for Jack. So he's got a 56% in this sample here, so 0.56. That's his p hat. So should he be confident based on that 0.56? So that's the question. So there's two explanations we can get for why we observe a 56 out of 100. One of the explanations is that 56 out of 100 just happened by chance. So it's a likely result if the true population value were 50%. So it's just a likely result to observe that in a sample, so he should not be confident. The other explanation is maybe that result is not likely to happen. It's not likely to just happen by chance alone. So then maybe more than 50% do actually support Jack, and therefore he should be confident of victory. So what they've done here is so instead of like calculating the p-value or probability like I showed you here in these notes, what they've done here is they've simulated using a software 400 samples size 100 from a population in which exactly 50% of the voters support Jack. So just imagine you've got this big entire population here, and in that population 50% of them actually support Jack. And then you take a sample of size 100 and you look for the in that one sample the proportion that will vote for Jack. Put that sample back. Take another sample of 100. Look for the proportion that will vote for Jack. And you keep doing that until you get 400 samples. So all these dots down here represent the results of each one of those samples. So if you look here at the dot, so if we look at 0.56, here's 0.56. This is not that unusual. So if 0.56 was considered unusual, so would 0.57 or 0.58 or 0.59 and so on. So I'm not going to look at what's the likelihood of just 0.56. I'm going to look at 0.56 and anything higher than 0.56. So if I look at that here, all those samples right there, that's 13.75%. So 13.75% of the time, we could get a result, a sample result that would have a p-hat of 0.56 or larger. I am going to say that that's not that unusual. So since it's not that unusual, so he observes that from one sample. So it's not that unusual for me to observe a value like that. So therefore, the fact that he observed that is just probably due to chance, and he shouldn't be confident of victory. So another way we can think about it, if we're thinking about what does that probability mean? So there's a 13.75% chance of obtaining 0.56 or higher, and this is from the sample, if the true proportion were 0.5. It's very likely for me to observe that value in a sample. So since it's so likely for me to observe that value, I don't think he should be confident of victory. All right, so here. So just like we did when we did this little introduction here, we had two hypotheses. So we had an HO and an HA. HO is your null, HA is your alternative. So the null is the one that you're trying to find evidence against. And the null is your statement of no difference. So it's like your status quo statement. Your alternative, your HA, is the one you're finding evidence for. So the null, HO or H naught, the alternative, HA. What are some common mistakes? So whenever we write out these hypotheses, we always use parameters. So we use population symbols, so like P, or we might use mu, or we could use sigma. We don't use the statistic symbol, so we don't use x bar or p hat in those hypotheses. we have one-sided and two-sided alternative hypotheses. So that HA. So in this one right here, this is just going in one direction. So this is a one-sided. So one-sided is like greater than or less than. The two-sided is not equal to. If you notice here, it's the HA. It's the HA, the alternative, that has the greater than, the less than, the not equal to. It's not the HO. The HO is always going to, in our textbook, the HO is always going to be equal. How do you decide which way you're going to go? You got to read, look for keywords. All right, so when we write out the hypotheses for Jack's mayoral race, so we're testing the proportion. So when you write out the hypotheses, this will be step 1 of your 4-step procedure. So P, it's the proportion. You're going to define the parameter here. So I'm going to say P is the, I'm going to add a word here because I should have this word in here. So P is the true proportion of voters who will vote for Jack. So you want to define the parameter. That's going to be your step 1. HO, P is just equal to 0.5. HA, P is greater than 0.5. Remember back here, Jack was trying to test. He wanted to know if he had more than 50% of the vote. So more, greater than. All right, so that's my hypotheses. All right, you can read this problem here about Mike being the golfer. You might want to pause the video until you get the chance to read it, because I'm not going to pause. I'm just going to keep talking. So in this one, we're actually testing the standard deviation. Again, you should have read it, because that's going to really help you if you read the problem and then you're listening to my answer. So it's standard deviation. So again, I need that word true in there. I always forget that. It's the true, actual. So it's the true standard deviation of this distances. That's what we're testing here. Remember, sigma is the parameter. That's the symbol I use for the population. We're not using SX here. So the hypothesis, he is hoping that his new shots will make him more consistent, so less variable. So his null is that he's equal to 15. The alternative is that he's less than 15. All right, go ahead again. Read this example, pause the video, take some time to read it, and then unpause the video to listen to me again. All right, in this one, we're testing the weight. So it's the true mean weight of the pineapples. The appropriate hypotheses for performing the test. So again, there's my equal. HO equal to 31. And this one just says effect. Now, obviously, you probably think they're trying to get fatter pineapples. That's your opinion, though. We don't know. The problem just says we want to know if it affects it. So effect, not equal to. All right. So this first section here, it's just kind of like, it's not really doing all 4 steps. We're just kind of defining some things. So another definition we have here is the p-value. So we talked about this a little bit in our introduction, but the p-value is the probability of getting the sample result or something more extreme. Now that more extreme, it's always in the direction of HA if HO is true. So how to interpret it. So this is the statement here that I want you to actually just write down, and I want you to use if you're ever asked to interpret a p-value. So there is a blank chance of observing a sample result of blank or more extreme if the true parameter were blank. All right, so I shortcutted it a little bit before just because we weren't quite there. So here, I'm going to add something. There is a 0.159 chance. This is from our intro problem. This is the p-value we got. So the 0.159 chance of obtaining a sample proportion p hat of 0.55. Now remember, my definition says or more extreme. You can leave it like that, just say or more extreme. But in this problem, I know that it's greater than a 0.55 or higher if the true proportion were 0.5. Same thing over here, 0.88 or higher. Because it's the probability of getting that value or something bigger. In this case, I'm doing bigger. If my HA was less than, then it would be that value or something smaller. If my HA was not equal to, it would be that value or something more extreme in both directions. All right, so that's a statement you want to remember. So here's Mike. There's his p-value. So again, I'm going to take that statement up there. So interpret it. There is a 0.0002 chance, I'm just plugging everything in here, of observing a sample result. So I just said here, I said a sample standard deviation of 10.9 or less. Since it's less, because it's HA is less. If the true standard deviation were 15. Okay, so parameter is the true standard deviation here. All right, do the data provide evidence against the null hypothesis? All right, think about what this is saying here. It is not likely for him to observe this sample standard deviation if this is the true standard deviation. So yes, I have evidence against this because it's not likely for me to see this value if this were the true value. So since it's not likely for me to see that, I can say yes, the p-value is small, indicating the result is unlikely to occur by chance alone. It's not likely for this to happen. That leads me into my next down here, where I'm going to talk to you about what do you conclude when you get that data. So your two possible conclusions are that one, your p-value is small, so we reject the null. P-value is large, we fail to reject it. All right, what do I mean by small? What do I mean by large? Well, I'll get into that in a second. What are some common errors that students make in their conclusion? You always want to write that final statement. Again, we're not there yet, but you always want to write it in context, and you never want to say you accept HO. I'll tell you why in a little bit. All right, like I said, what is small? What is large? Sometimes small is easy, like this is small. Sometimes large is easy. But sometimes it's not so easy, like when you get 0.07. Is that small? Is that large? I don't know. So sometimes what we do is we use a significance level. So a significance level is just a cutoff. So it's a cutoff for our p-value. So the symbol that we use for a significance level is alpha. It's a Greek letter. So when are the results of a study statistically significant? When your p-value is less than alpha, then your results are statistically significant. These are the most frequently used levels of alpha. So back to Mayer, to Jack for Mayer. Here's his p-value. This one right here, pretty high, so it says here it's large. Again, if this is my, this is usually our maximum cutoff that you'll see. So this number is bigger than that. So then I would do something called fail to reject, and I can't conclude that more than 50% of the voters favor Jack. If this one with Mike, his p-value is small, so then I reject, and I can conclude that he's more consistent. I'll go over the fail to reject and reject on the next page. Okay, this example right here is just doing conclusions here. So if your p-value, so let's just go through this. If your p-value is less than your significance level, so your p-value is small, you're rejecting HO, and you can conclude HA. If your p-value is greater than or equal to alpha, you're going to fail to reject HO, and you can't conclude HA. Okay? All right, so again, pause the video, read about Xenon and his potato chips. All right, so he gets this p-value. What conclusion would you make at each of the following significant levels? All right, if you notice here, I try to also make this pretty standard for you. So in this case, if this is my significance level, so this number is less than that, so the p-value is less than alpha. So if it's less, I'm rejecting HO, and then I can say there is enough evidence, and I'm putting this in context. There is enough evidence to conclude, so P, the proportion of students at his school that prefer name brand chips is greater than 0.5. So this right here, it's all what that HA is saying. So I can conclude HA. And this one, this is a really small significance level. We are not less than that. So my p-value is greater than alpha, so I fail to reject. And then there is not enough evidence to conclude, and this would say the same thing. There's not, but now I have the word not in there. Not enough evidence to conclude the proportion of students at his school that prefer name brand chips is greater than 0.5. Okay? Tomorrow, the next few days, we'll put it all together. Right now, we're just kind of talking about the pieces. All right, let's say we were at a jury trial. So we could have two errors, right? So we could let a guilty person free or put an innocent person in jail. So in a significance test, we can make two kind of errors. We can make a type 1 and a type 2 error. So a type 1 is we reject a true null hypothesis. Type 2 is we don't reject. So we fail to reject a false null hypothesis. Which error is worse? It really just depends. This chart right here, you just kind of want to memorize or remember this chart. So you've got your conclusions, reject HO, fail to reject. We've got what's actually true. Remember, we are taking a sample. So we're taking a sample and we're trying to infer something about the population. We can be wrong. Like, this is not exactly the same thing as the population. There is a chance that we made an error. We're not going to know if we made that error or not. Maybe later on, after we roll out like a new drug, or we, roll out a new product after we tested quality control. Like, we're not going to. At some point, maybe we'll figure out. We'll get customer feedback or performance or whatever. But at the time that we do the test, we don't know if we made that error or not. So if we reject HO, but it was actually true, that's your type 1 error. If we don't reject it and it was actually false, that's a type 2 error. Again, the severity of it just depends on the situation. As before, pause the video, read about our fast food problem, and then we will discuss our type 1 and type 2 errors. All right. So type 1. So if in a type 1, I'm rejecting HO, but I shouldn't have. So if I reject HO, I'm actually going to conclude HA. It says describe the error in this setting. So there's your context. So don't just say reject HO, but it's true, and explain the consequences. Okay, concludes the proportion of drive-through customers who wait has reduced, but really it has not. So a type 1, I reject HO, so I'm throwing this out, I conclude HA. So then I conclude the proportion who weight has reduced, but really it didn't reduce. So I shouldn't have really done that. Consequence. So he had hired an additional employee to reduce the wait time. So I'm going to keep that employee, but he really is adding no value. Type 2 error. Concludes the proportion has not been reduced, but really it was reduced. So again, a type 2 error we don't reject. So I don't think I reduced it, but I really did reduce the proportion. So I get rid of the employee because I think he's not adding any value, and the customer wait times stay high or go back up. Okay? All right. This last stuff here is just kind of some stuff I want you to realize. You're only making a type 1 error if you reject your null. You're only going to reject your null if your p-value is less than alpha. So therefore, that alpha, whatever that number is, that's your probability of your type 1 error. Because again, you're only rejecting if you're less than alpha. So here, if you're using, for the fast food problem, if you're using an alpha of 0.1, the probability of making that type 1 error is just the 0.1. So obviously, you can reduce a type 1 error by lowering your significance level. So if I'm not happy with my consequence of the type 1 error, I'll just lower the significance level. But I might not want to do that because if I lower my significance level, If I lower my type 1 error, I increase my type 2 error. Okay, these are inversely related. All right, so the symbol for the type 2 error is beta. It's a little bit cumbersome to calculate, and it's just beyond the scope of this. I mean, you could do it, but it's beyond the scope of the AP curriculum. But a type 2 error, so remember, you're failing to reject, but it's false. So given that it's false, what's the probability I fail to reject? So that's your type 2 error. Then there's something here that's called a power. So this is if I do the complement of this, so if I do 1 minus beta. All right, so again, given that the null is false, I have two options here. I fail to reject, or I reject. If the null is false and I fail to reject, then that's a bad thing. So that's my type 2 error. If the null is false and I reject it, that's a good thing. I've done the right thing. That's called power. Okay, that's how good your test stat is rejecting when it should be rejecting. So all these three things, your type 1 error, your type 2 error, and your power, they all kind of are working together here. And depending on what your goal is at the start of the test, one of them you might be trying to increase or decrease, okay? Again, it's a little bit cumbersome for us to calculate, so we're not going to worry about it. It's just here. All right, so just to summarize everything, you've got your type 1 error, which is alpha, your type 2 error, which is beta. The power is 1 minus that, okay? Over here, I'm going to make a little chart. So as your power goes up, your type 2 has to go down. If this is bigger, if this answer is bigger, the only way I made that bigger was by making this smaller. Bigger, smaller. But if I made this smaller, then I increase my type 1. If my power goes down, so if I make this answer smaller, then I had to have made this bigger. And if I made my type 2 bigger, then I made my type 1 smaller. So the type 1 and type 2 errors, so these ones right here, are inversely related. Power and type 1 are always going in the same direction. Okay, power and type 2 are also inversely related. All right, if you want to increase your power, so if I want to increase my power, I'm going to increase my alpha, because that increases my type 2, and then it'll increase my power. Or you can always increase the sample size. Bigger samples always are more powerful, okay? All right, that's your homework.